Okay, guys, I'm just closing this up and we're going to start our Punnett square and pedigree lesson here. I need you to get your textbooks out. Every single person needs your textbook out, and we are going to go through this. The slides themselves are not long. I think there's only 5 or 6 slides. They're not long at all, but there's a lot of practicing. So I really need everybody to have their textbooks open to page 340. If you haven't got your textbook, please go get it. If you need to pause this video while everyone gets their textbooks from your locker, your cubby, wherever, everybody needs a textbook, okay? So you guys did your Engage Your Brain and the active reading yesterday. Oh no, not yesterday. Yes. After your quiz. So you should have had that done. So we are not pausing to do that by any means right now. You already have that done, and you should have gone over that potentially together as a class yesterday. If you didn't, excuse me, you can do that quickly now. Okay, so everybody needs to have their page open to page 340, and you are going to need a pencil. You know I don't like pens, so please have a pencil out. Everybody needs to have a textbook, okay? So we are going to talk about Punnett squares, and some of you guys have seen me write Punnett squares on the board, and some of you may have done a little bit of this in the past, especially if you are new this year. You may have done it in the past at another school. And so Punnett squares are fun. I think they're fun. But they are a graphic organizer pretty much. And so they are a tool that scientists use and we use to just simply predict the possible genotypes of an offspring. Remember, genotypes are the letters. And then the genotype will tell us what the phenotype is going to be. Remember, genotype has the gene, so it has the letters. And phenotype is like the photo, it has the pH, okay? And it's going to be able to tell us the possible genotypes of offsprings in any given cross for the most part. We're right now only going to look at really basic 2-letter crosses. So single traits. We may dabble in a little bit with our labs, maybe do a double trait, like take our pea plants and do purple, like do flower colors and where the flowers are positioned on the plant. But right now, while we're learning about this, we're just going to simply use one trait at a time. And so you remember that each parent has 2 alleles for a particular gene. Okay, so you can kind of see up here in this one, you see how it's got 2 capital B's, capital B lowercase b, capital B lowercase b, and 2 lowercase b's. Okay, so that is 2 alleles. So up here, the parent, capital B, lowercase b, capital B, lowercase b. So this is the parent. Okay, so an offspring receives an allele from each parent. Okay, so it receives this allele, and then this is its offspring. So Punnett square shows all of the possible allele combinations in the offspring. Does that mean that every single offspring, so let's say if somebody has 4 kids, are they going to definitely see these 4 genotypes? Not necessarily. Okay. They may have 4 kids and only see this phenotype or whatnot. And so it's just showing you the possible combinations. Okay, possible. Not the ones that are definitely going to occur. So take a look at that Punnett square on page 340. And this shows how alleles are expected to be distributed in a cross between a pea plant that has purple flowers and a pea plant with white flowers. Okay, so how you set this Punnett square up is you can see right there. Look at page 340 and you can kind of see this box. And so you see the 4 boxes there in the middle. And then above that, you see 2 letters. And on the left side, excuse me, it's really late on Monday night. You see 2 letters. Okay. And so what this is that one parent's alleles are going to be on the top and one parent set of alleles are going to be on the left. And you kind of separate them. Okay. And so that they are over or next to the sets of boxes. Okay. So this Punnett square shows the possible offspring combinations in pea plants with different colors. So this is showing you all the possible offspring that these plants could have. Now, think back to our heredity section last chapter, and we talked about true breeding plants. And we talked about the fact that true breeding plants can only produce that trait because that is the only letter, the only gene, the only allele that it carries. So that top plant, the capital F and capital F, is a purple flowered plant. I'm not really sure why they use F's here. I would have used P's. The problem with P's sometimes, though, is that it's hard to tell between the capital and lowercase letters unless they're right next to each other. So that is maybe why they used F's. Some letters are hard to tell the difference between unless they're right next to each other. So like S's and C's and P's and are sometimes U's, W's, X's, things like that. Z's are often hard to distinguish between capital letters. So if you are the one choosing the letters, choose letters that are very easy to distinguish between capital and lowercase. A's, B's, D's, H's, K's, L's, things like that. Okay. Anyways, moving on. So you can see that top plant is the true breeding purple flowered pea plant on the top. You can see that your parent on the left there is the true breeding white flowered pea plant. It only has the lowercase f's. That's all it has. Okay. So it can only pass on lowercase f's, which means it can only pass on white flower traits. And the purple flower can only pass on capital F's, which means it can only pass on purple flower traits. Okay, does that make sense? I can't see your faces, so I'm hoping this makes sense. Okay, so when they cross, so you've got your parents on the top and you got your parents on the side. And you see the purple, see how they're in purple and they're in blue. So what happens is that the parents on the top give a capital F. So let's look at the parent on the top. There's a left and a right one, right? Correct? So that F on the left can give an F, a capital F to the 2 boxes below it. That's it. And then the F on the right can also only give a capital F to the 2 boxes below it. Okay, do you see that? Do you see how that purple arrow is pointing down? And then the lowercase blue f's, okay, there are lowercase f's, they can only go to across from them. Okay, so the lowercase blue f, do you see how it can only give it to the boxes to its right? And then the one on the bottom can only give its light blue f to the 2 boxes to its right. Do you see that? Again, I hope you see that. So When it combines, you have a capital F and a lowercase f in those boxes. Do you see that? Which then means when you look at those capital F and lowercase f, every single one of those offspring is purple. Because if you again remember in the heredity section that we just learned about, that if there is a capital letter in the genotype, it is going to be a dominant phenotype. If there is, I'm going to say that again, if there is at least one capital letter which represents a dominant trait somewhere in the genotype, then that phenotype is going to have that dominant trait. Every single one of these boxes, the shaded in boxes, have a capital F, which means that every single one of those offspring are going to be purple. There will be no white flowers in this first generation because we had a true breeding purple flowering plant, which means that it can only pass on the purple flowering trait. And purple is dominant to white, and it is going to mask and hide our recessive trait. Okay? So let's look at page 341 and visualize it. You guys are going to do this. So I want you to fill in the genotypes and the phenotypes of the parents and offspring in this Punnett square. You're going to then sketch the resulting offspring possibilities in the white boxes. Okay? We're going to assume absolute, complete dominance. So no codominance, no incomplete dominance, complete dominance. Okay, look at the key over there to the left and notice that the capital letter stands for round P allele and that the lowercase r stands for wrinkled P allele. So think about what the parent on the top, what its genotype is, and it gives it to you if you look right above the boxes, and what that phenotype is actually. And again, if you look at the P right above that, you can see what it looks like. Really easy. Same thing for the P on the left. What is its genotype? Look at the blue letters. What's its phenotype? Look at the P itself. Do not abbreviate. I want you to write out round P allele, wrinkled P allele. Then you're going to take that first box, the top left box. We always start there. We go across and then we go to the left like you're reading, okay? Left to right, down, left to right. So start in that top box. Take the letter that is directly above it, put it there, and the genotype. Take the letter that is directly to the left and put it next to the other letter. What do you get? Those two letters are the genotype. What kind of phenotype do those two letters create? And then sketch it in that picture. Now you're going to move to the right, okay? And like I've told you before, you're always going to put the capital letter prior to the lowercase letter. It does not matter if you start with the top offspring or the left offspring. It's not going to matter. I usually do the top offspring first, but again, in this case, you would do the top letter and the left letter, but you have to make sure you put the capital letter first. Okay. Again, write that in the genotype. What kind of a phenotype is that going to make? Sketch it in that picture. Go to the bottom left. Take the top letter, pull it all the way down. Take the left letter, pull it over. What is your genotype? What is the phenotype? Now take the last box. Take the top letter, follow it down. Take the left letter, bring it over. What's your genotype? What's your phenotype? Sketch it. When I see you on Friday, we will go over this because I don't want to tell you now and have you just wait for me to give you the answer. Okay? Then I want you to take number 7 and analyze it. What does each compartment of the Punnett square represent? So think back to the notes. Look back through that page 340. What does it represent? Okay. Okay, turn the page. We're on 342. So, how can a Punnett square, be used to make predictions about offspring? First of all, a Punnett square does not tell you what the exact results of a cross is going to be. Okay, it is not going to tell you the exact results. Okay. It is not going to tell you how many kids your parents have, how many kids you may have or your parents have are going to have blue eyes, okay, or brown eyes or whatever. Now, there are in certain cases you will know, okay, like I said, my husband and I both have blue eyes. We can only have blue-eyed kids because we only carry blue-eyed traits. But if I married a brown-eyed guy, I don't really know. Could have had only brown eyes, could have had some blue and brown eyes, could have had all blue eyes. Not sure. The Punnett square just tells you what you could have, what the possibilities are. It only helps you find the probability that a certain genotype will occur. Okay, so that cross that you did, or the cross that's down there on page 342, you can see the outcome. We're going to do that one in a second. Probability is the mathematical chance of a specific outcome in relation to the total number of possibilities. So you're like, what does that mean? Let's break it down to super simple terms. Take a coin. A coin has two sides, heads and tails. So what is the probability that you are going to flip heads? 1 out of 2. You have a 50-50 chance that you are going to flip your coin and it's going to land on heads. Every single time you flip that coin, you have a 50-50 chance because there are only 2 options. That's probability. Now, if you say, what is the probability of flipping heads twice in a row? You multiply, and this is something Dr. Zukin can help you with if you're really confused, or Mrs. Sockman, okay? But then that becomes 1/4. Okay, you multiply the probabilities by each other. So if it's 1/2, and you would multiply it by 1/2, you would get 1/4. So you'd have a 1 in 4 chance of it flipping heads and heads, because you could have had heads and heads, heads and tails and tails, or tails and heads. So there were 4 options, and only one of those was heads and heads. Okay. So again, if you try to say, well, what's my probability of doing heads 3 times? Well, what's a half times a half times a half? Okay, that would become like 1/8, I think, if I'm doing my math right in my head quickly. Does that make sense? So that's probability. Again, if you roll a dice and you're like, oh, I want to roll a 2, you have a 1 out of 6 chances to roll a 2 because there are 6 sides to that dice. Okay, does that make sense? That's probability, the mathematical chance of a very specific outcome occurring in relation to the total number of possible outcomes. So again, Super Bowl, Bengals versus the Rams, there was a 50-50 chance. There was only 2 teams. One team was going to win. One team was not going to win. Now, you can throw in a whole lot of other things and get really specific with, all the statistics. But we're not going there. We're just saying each team had a 50-50 chance of winning because there's only 2 teams. Okay? Makes sense? So probability is the mathematical chance of a specific outcome in relation to the total number of possibilities. So if you're looking, let's flip back real fast to page 340. The probability of having purple flowers is 100%, is 4 out of 4. That is the only probability that I could get. Because I only have one possible outcome, I can only have one specific outcome. Okay? There was no way I was going to get white flowers out of that. So this was a 4-0 ratio. We often write probabilities in the forms of ratios. That's why I said you have a 1 out of 2 probability of flipping heads. So that would be a 1-to-2 ratio. Okay. The only ratio again here is a 4-0. 4-0 purple flowers to white flowers, or 4-0 of capital F lowercase f. Well, this would be different. This would be like 4-0-0-0. No, 4-0-0. Okay, and I'll explain that in a minute. Okay, so flip back. Sorry, 342. So a ratio is often written as one number to another number. Sometimes, and we will see this again, you will see this as we go through, that sometimes it'll be a 1, like a number to a number to a number. There'll be 3 options. There could be 4 options. The ratios obtained from a Punnett square tell you the probability that any one offspring will get certain alleles. So, I do want you guys to understand something. Okay. Trying to see. That you will see sometimes 2 different ratios. Okay. And I'm looking real fast as I'm sitting here. I'm glancing through the book. Okay. They don't really go into it, but I want you guys to know this. There are 2 different types of ratios. And I know that right now it doesn't. Yeah. So anyways, so there is I'm going to, now that I'm doing this and explaining it to you, I realize that I need to put this in the notes. So in the slides, now that I'm presenting this and I don't have it, and I apologize, right here, I am going to write an extension that says genotypic ratio and phenotypic ratio. So you'll see that in your notes, and that will be in the slides, like the slides themselves. But unfortunately, I don't have it here in the presentation. But know that it's going to be right here. So if you're like, my notes don't match the Mrs. Stewart's lesson, it's because I'm realizing now as I'm doing this that I really need to put that in there. So when I mean that there are 2 ratios, and there's a genotypic ratio and a phenotypic ratio. What I mean by that is there's going to be a ratio to the genotypes, which are my letter combinations. And then there's going to be a genotype to what I see in my phenotypes. So just looking at 342 and 343, what I mean by this is take a look at, and I know we haven't done these, do the math. I'm going to have you guys do this. I see these ratios that I'm talking about right there. So that's what I want to look at real fast. So look at the Punnett square there on 342. Let's take a look at my ratio, my genotypes for my offspring. How many capital B, lowercase b combinations do I have? 2, right? Capital B, lowercase b. I have 2 of them. And how many little b offspring do I have? 2. So my genotypic ratio is 2 to 2, or I can reduce that to 1 to 1. Okay, you do want to, it's just like a math, simplify, simplify, simplify. You have a 1 to 1 ratio. Okay, you have, I think those are guinea pigs, and you have a black guinea pig and a brown guinea pig. This is their fur color. So you have a 1 to 1 ratio to like a 2 to 2, simplified down to 1 to 1 ratio for my genotypes. Now let's take a look at my phenotypes, which is what do I actually see with my 2 eyes? I see 2 black guinea pigs. Just look at the pictures. Don't look at the genes right now. And I see 2 brown guinea pigs. How many black guinea pigs do I have? 2. How many brown guinea pigs do I have? 2. So what's my ratio? 2 black guinea pigs to 2 brown guinea pigs. Simplify 1 to 1. So my genotype and my phenotype match right here. We have a 1 to 1 ratio, right? Because I have 2 capital B, lowercase b to 2 lowercase b. Simplify to 1 to 1. I have 2 black guinea pigs and I have 2 brown guinea pigs. Simplify 1 to 1. My ratios match. Take a look at page 343. Let's look at just the genotypes right now. Do not look at the pictures. Well, it's hard to really not see them, but focus on the letters. How many capital B combinations do I have? 1, right? How many capital B, lowercase b combinations do I have? 2. How many little b combinations do I have? 1. So in this case, I have a 1 to 2 to 1 ratio for my genotype. Okay. Do you see that? That's my genotypic ratio. 1 to 2 to 1. 1 capital B, 2 capital B, lowercase b's, 1 lowercase b. That's my genotypic ratio. Okay, now let's look at our phenotypic ratio. How many black guinea pigs do you see? 3. How many brown guinea pigs do you see? 1. So my phenotypic ratio is a 3 to 1. 3 black guinea pigs to 1 brown guinea pig. My genotypic ratio is 1 to 2 to 1, but my phenotypic ratio is 3 to 1. Do you see that how there are different ratios? So you want to make sure that you are understanding which ratio questions are going to be asking you for, the genotypic or the phenotypic ratio. Sometimes, like on 342, they're going to match. Sometimes, like on page 343, they're not going to match. Okay? Does that make sense? Again, I can't see you, so I have no idea if you actually do get this. If this does not make sense, I will be there on Friday, or you can email me and I can try to make a video of potentially a video of me actually writing out the genotypes and the Punnett squares and stuff. Okay? So, another way of expressing probability is as a percentage. You guys heard me say that you had a 50-50 chance. So it literally states the number times a certain outcome might happen out of 100 chances. Okay. So what that simply is, so let's say we have a 1/2. So you're going to take your ratio and you're kind of going to flip it. So that the first number's on the top and the second number's on the bottom. Okay. Does that make sense? In this case. So it's 1-4. Again, I think you guys have done percentages. I think you may have done some probabilities. Again, we can do some of this. I can do some of this on a video. You can ask Dr. Zugan. You can ask Mrs. Sockman. So then you're going to think, okay, this bottom number, the denominator, how many times does it take to get to 100? So 4 times what gives you 100? How many? 25 times, right? So then my bottom number becomes 100, and then my top number becomes 25, because what's 1 times 25? 25. So if I do something 100 times, when it is a 1-4 ratio, it means I want to get my outcome 25 of those times. Okay? Theoretically and probability wise. So if you were to take, I don't know, you don't really have 4-sided things. What's something that's 4-sided? Drawing a blank right now. Okay. I don't know. Anyway, okay, I've got this. If you have a quarter, a penny, a nickel, a dime, and a quarter in your purse, and you pull one coin out, you pull a coin out of your purse 100 times. 25 of those times, you will pull out that quarter. Does that make sense? That's my ratio as a percentage. That'd be 25% of the time I will pull out that quarter. Okay. That is why I say when you flip a coin, it is a 50% chance that you will get heads. Because 1/2, 2, to get to 100, you have to multiply 2 by 50. And if I multiply the bottom by a number, I have to multiply the top by a number. So 1 times 50 is 50. So 50 over 100, you can say as a percent, anything over 100 can be a percent. Right now, that's what we're saying. So that would be 50% of the time. If something is 90 over 100, that would be 90% of the time. Okay. So now let's actually do the math on page 342 and 343. Okay. So, oops, sorry. I did not mean to go to that next page. So let's look at page 342. Let's look at that, do the math. In guinea pigs, the dominant B allele is responsible for black fur, while the recessive little b allele is responsible for brown fur. Use the Punnett square to find the probability of this cross resulting in offspring with brown fur. So, letter A. What do you know? That parent genotypes are B, capital B, lowercase b, and little b, little b. Possible offspring genotypes are big B, little b, and little b. What do you want to find out? The probability of the cross resulting in offspring with brown fur. So you're going to count the total number of offspring allele combinations, which is 4. Count the number of allele combinations that will result in offspring with brown fur. That is 2. Write the probability of the offspring with brown fur as a ratio, 2-4. Rewrite the ratio to express the probability out of 100. Offspring by multiplying each side of the ratio by the same number, such as 25. In this case, 4 times 25 gives you 100. The top number is 50. So we convert this to a percentage, 50%. Now I want you to do number 8, calculate. This Punnett square shows a cross between two Big B Little B guinea pigs. What is the probability of the cross resulting in offspring with black fur? So you're going to do C, A, B, C, D, E, F, and G. And yes, it's a little different. You have 3 numbers this time, but think about it logically. You have 3 numbers. You have a 1 to 2 to 1 ratio, and they have to add up to 100. Okay? So think about which number am I going to multiply by that's going to give me 100. Okay? Does that make sense? Think about that. Again, I'm not going to give you the answer. I will give you the answer when I see you on Friday. Then, number 9, graph. In the cross above, what is the ratio of each of the possible genotypes? Show your results by filling in the pie chart right there at the right. Fill in the key with color or shading to show which pieces of the chart represent the different offspring genotypes. Do not scribble. I want to see a good pie chart there. So either use 3 different colors or 3 different shades of your pencil, because you can't shade very well with a pen. Okay. Let's move on to pedigrees. So, pedigrees, how can a pedigree trace a trait through generations? This is a beautiful pedigree. Oh, look, there's those words I taught you, homozygous and heterozygous. Okay. So a pedigree is another tool that we use to study patterns of inheritance. And it can actually trace the occurrence of different traits throughout I cannot talk, through generations of a family. So pedigrees can be created to trace an inherited trait, even your hair color. Okay? So I have no idea what that pedigree is for. But anyways, it's obviously some kind of animal because there are wild. Well, it could be a plant as well that you're crossing. Okay. Pedigrees actually are really useful in tracing what we call, sorry, that is a word spelled wrong, class of inherited disorders known as sex-linked disorders. And the reason that these are really good for sex-linked disorders is because you can tell on the pedigree which ones are males and females. Males, for whatever reason, are always going to be the boxes, and the females are always going to be the circles. So in this case, this is the dad, and this is the mom. Or in this case, grandpa and grandma. And they had, so you see this line means that they were joined together, and then this is their offspring. So the ones that come off of the line are their offspring. So they had 3 daughters. No, wait. Daughter, son, daughter, son. See that? See that? And this daughter got married. This son got married. This daughter either got married, did not get married, and just stayed single her whole life. She may have died at birth. She may have died young. It doesn't really tell us that. And then this son got married as well. We're going to go, I know I say married, but we don't really have wild types of people. So we're going to go with crosses of plants. Okay, so these plants were crossed and had 4 offsprings. This plant died. That's what we're going to say. Okay? Okay. Okie dokie. And so these were both heterozygous. So in this case, they got the dominant trait, but not the wild type, which we're going to say is the dominant. But anyways, you guys can kind of see. Then those cross and they had offspring. Cross, offspring. Cross, offspring. Okay? See how that works? Okay. So we have sex-linked disorders such as hemophilia, and color blindness are caused by an allele on the X chromosome. And you're like, well, why do boys have it then if it's on the X chromosome? This is why. Women, we have 2 X chromosomes. So we can only receive one allele, one X chromosome allele that could have color blindness on it. Because if our mom passed that on to us, then we got our X chromosome from our dad. But yes, women can get it because they would have to get the X chromosome from a color. If the dad was colorblind and the mom was a carrier for color blindness, then they could have a colorblind daughter. But what happens most of the time is that because the male only has one X chromosome, it does, and its color blindness is recessive. So actually, no, I'm not sure if it's recessive or dominant. Yes, it's recessive. I do know it is recessive. Because the male only has one X chromosome, it's going to show color blindness because it doesn't have that second X chromosome to mask it. It has a Y chromosome. Does that make sense? So a woman who is heterozygous for this trait is called a carrier because she can carry or pass on the trait. So let's look at this pedigree and let's completely ignore this wild type down here. Let's say that this red is non-colorblind and blue, actually, let's go the other way. Let's go with blue being non-colorblind and red being colorblind. Okay. I'm trying to think if that's going to work. I may have to actually draw this out for you guys, but up here you can see, let's not even look at colorblindness. Let's just see that they have a trait. Okay. Red means that they have it. Blue means that they don't. We're not going with the sex-linked disorder right now because then that pedigree is going to look different. So these 2 are carriers. They produce a child without, because I said this is without, this is with whatever the trait, whatever the disease is or trait is. Without it. Carrier, with it. Okay. She marries somebody who is a carrier. Okay. The carrier and she that does not have it, doesn't have it, carries it. These 2, neither one of them have it, so their children cannot have it in this case. This case has it, doesn't have it, and then they have 2 carriers and 2 ones that don't have it. So you see how that works? Okay. So let's take a look at the pedigree on 344 that traces a disease called cystic fibrosis. Cystic fibrosis causes serious lung problems, and most people that have cystic fibrosis do not live very long. They don't, it's getting to be more common for people to live longer, but it's usually referred to as like a child's disease. I have a friend who's actually in her 40s and has it. And she actually still goes to Nationwide Children's Hospital to be treated. Because it is so rare for people my age and her age to still be alive, honestly. Usually it requires lung transplants, and she hasn't. It's absolutely amazing. God has really, really done some miracles with her. But anyways, so they do not, carriers of the disease have one recessive allele. They do not have cystic fibrosis, but they are able to pass that recessive allele on to their children. If a child receives recessive allele from each parent, then the child will have cystic fibrosis. Other genetic conditions follow a very similar pattern. So let's take a look at this. Let's visualize this, okay? So up here at the top, again, squares are males, circles are females. Vertical lines connect children to their parents. Horizontal lines connect family members. So our top first generation are both carriers. Okay, so let's look at the key over there. A solid square or circle indicates that the person has a certain trait. A half-filled square or circle indicates that the person is a carrier of the trait. The empty ones mean that they don't have the trait. Okay, so we have two carriers, and they have 1, 2, 3, 4, 5 children. First child does, so just kind of look at that, figure out. So we're going to go through second generation there. Child 1 does not have it. Child 2 is a carrier. Child 3 does not have it. Child 4 has cystic fibrosis. Child 5 is a carrier, but marries somebody who does not have it. Okay? So then question 11, does anyone in the third generation have cystic fibrosis? So take a look at that. And then number 12, calculate what is the probability that the child of 2 carriers will have cystic fibrosis. So again, think about your probability. Okay? So that is the end of our notes. I said, you guys will have a couple days worth of different activities to go through Punnett squares and pedigrees. You'll have a lab that has pennies. You'll have a lab that has dice, so on. So you'll really get to understand that. Please email me if you are confused with Punnett squares or pedigrees, so that I can potentially make a video that you can see me, maybe with a dry erase board, actually trying to walk you through these. I know it's hard that I'm not writing up on the board. You know, if I were there, I'd be writing lots of stuff on the board, drawing lots of pictures. Practice the Punnett squares and whatnot. I said, because you will be doing some on a project we'll be doing next week, and so on. So please, please, please email me with questions. Anytime that you're confused, I can make another video that you see me actually doing these Punnett squares. If you have access to YouTube, by all means, Amoeba Sisters. You guys know that I love Amoeba Sisters. Amoeba Sisters, if I remember correctly, potentially has been, their videos are approved on YouTube. So I don't know if that means that you can access them or not. I'm not sure how that works. But look up maybe some of them doing Punnett squares and pedigrees. Definitely, definitely would be worth that. Okay, so I'm going to get out of here. And you guys have a great